class on the floor, and it was mildly polar.
The intersection of lines. Now, in 2 dimensions, and you did this way back in grade 10 when you looked at lines, there's 3 possibilities in 2 dimensions. First of all, they could be parallel lines. And if they're parallel lines, they never intersect. Another possibility, well, here's some work though. If you wanted to find out if they're parallel, you set up your system of equations and solve, and you cannot solve them because everything disappears. For example, we have 2x plus 3y equals 4, and if I gave you the second line of 6x plus 9y equals 7, these 2 lines are parallel. They never intersect. If you try to solve them, for example with elimination, if I would multiply my top line by a -3 and keep my bottom line the same, and I add those together, I get the common fact that 0 is equal to -5.
No, 0 plus 0.
0 plus 0 equals -5. That is going to help you.
I'm going to put this on the exam.
Now, that solution is false. And if you get a false statement, so you cannot solve because the variables all disappear, and you get a false statement, that means that those 2 lines are parallel.
If it's a true statement, then will they be
If you get something like 2y equals 4, so y is equal to 2, then you have a situation where, well, they're concurrent. All right. So here is 2 lines in vector form. We want to show that they're parallel. You can see just from, if you take their direction vectors, how do we show? Put a k somewhere. I would say I like my k here. And then from my first equation, I would get 3k equals 6. In other words, aka k is 2. And in the second one, we get 2k is equal to 4, which also lets us know k is 2. And if there is such a value of k, then one vector is a scalar multiple of the other, and those 2 vectors are parallel. That's a 4. That is a very bad 4.
I'm not going to judge. You know what? Hey, at least they don't look like a 9. They used to look like 9s.
Yes, you could put it in front of the other one, right, JR?
Yes, and then you would get k as a half. And it really doesn't matter. I always put the k so that I don't get a fraction. I like to try to do that. Not always possible. Concurrent lines mean the 2 lines cross, and that single point where they cross will be the solution. So if you want to determine if their 2 lines are concurrent, you can set up your systems of equations. When you solve, and here I say when you solve for s and t, just like we did in our example before, where we had our parametric equations, one with s, one with t, you will get a unique value for s and t. You can plug that point in and find out where they intersect. So in 2 dimensions here, my 2 parametric equations, for my one line, I'll get -3 plus t and 5 plus 2t. For my second line, I will get 4 plus 3s for x and 3 minus 2s for y. Setting those equal to each other, I get -3 plus t is equal to 4 plus 3s, and 5 plus 2t is equal to 3 minus 2s. And we get a system of equations what I would do probably in this situation is I would multiply equation 1 here by a -2. Can you see if I multiplied equation 1 by a negative 2, my equation 1 would become positive 6 minus 2t equals negative 8 minus 6s. If I rewrote equation 2, 5 plus 2t equals 3 minus 2s, the advantage of doing this is if I add equation 1 to equation 2 at this point, my variable t will be eliminated. 11 equals negative 11 minus 8s. Did I make, oh, negative 3 plus 8 is, thank you, negative 5. Yes. And then we get nicer numbers. And there's a negative with the 8. And then becomes negative 2. So s is equal to negative 2. And since you have s is equal to negative 2, you could plug that back in to either of your equations and solve for t. So s is negative 2. Negative 6 plus 4 is negative 2 plus 3. T would be equal to 1. So because we're able to solve for s and t, we show that these two lines are concurrent. There is a point where they intersect, and I could plug in t equals 1 or s equals negative 2 and find that intersection point. The last possibility in 2 dimensions is that they're the exact same line. If you were solving this type of equation, all your variables would disappear again, but you would get a true statement. Some number equals some number, it's the same number. That's always true. And that would imply that things are coincident. So what's an example of that? We're going to show that those two lines are coincident. They're exact same line. So if I go to my parametric equations, for my one line I've got 1 plus 3t, and my other line I have 2 plus 2t. My second line I've got 7 plus 6s and 6 plus 4s. Which implies that 1 plus 3t has to equal 7 plus 6x, s, and 2 plus 2t is equal to 6 plus 4s. Now, sometimes you don't realize, and most of the time you will assume that they intersect at a single point. So at this point, you're going to want to solve for t, you're going to want to solve for s. Right, and so what you do is you say, okay, I want to eliminate one of them. Let's say I want to eliminate t. I could multiply equation 1 by a negative 2 and equation 2 by 3. So again, I'm using the elimination technique here. You could use a bunch of different techniques. But what this does is this gives me equation 1 becomes negative 2 minus 6t equals negative 14 minus 12s. And equation 2, when it's multiplied by 3, becomes 6 plus 6t equals 18 plus 12s. If I add those together, my t's cancel out. On this side, I just have 4. My s's cancel out, and on this side, I have 4 as well, which is a true statement, which implies that those two lines are identical. Okay? They don't look identical based on the equations, But if you look at the equations and the direction vectors, can you see they're parallel? And if t is 2, can you see that you get the point 7,6? So if they're parallel and they have a point in common, well, they must be exactly the same line. Yay. Now that is taking our two-dimensional stuff and talking about it. In three-dimensional, we have an additional case that could happen. Yeah. In three dimensions, you could get the same thing, lines being parallel and never intersect. You could get lines that intersect at one point. And you could also get lines that are exactly the same. But in three dimensions, you could have lines that aren't parallel, but still don't intersect. You think about airplanes flying through the sky, going in different directions, but they don't cross. Their jet streams never cross. Three dimensions making things more complicated. These lines that aren't parallel but don't cross are called skew lines. So we're going to find out, again, this is two-dimensional still. So for all of these questions, what we've been doing is we've been using our parametric equations. So for our first one, we would have 18 plus 3t and negative 2 minus 2t. Our second equations, parametric equations, are negative 5 plus 2 lambda. Why not, eh? 4 plus lambda. It's just a Greek letter. And so, we've got 18 plus 3t is equal to negative 5 plus 2 lambda, and negative 2 minus 2t equal to 4 plus lambda. If this is my first equation and this is my second equation, I'm going to take my second equation and I'm going to multiply it by negative 2, because that will cancel out my lambdas. So if I rewrote equation 1, I have 18 plus 3t equals negative 5 plus 2 lambda. And if I multiply equation 2 by a negative 2, I will get 4 plus 4t is equal to negative 8 minus 2 lambda. Add those two equations together. And so 7t is equal to negative 35. And t is equal to negative 5. Once we know that t is equal to negative 5, we can solve for lambda, and lambda would be positive 4. This means you could either use the t value or the lambda value to find your position vector of the intersection. So the position vector of our common point would be 3, 8. So to figure out 3, 8, I can plug in negative 5 in for t, or I could plug in 4 for lambda. And if you really want to check to make sure you haven't made any mistakes, it's not bad to plug in both, because you should get the same value. If you're getting different values, that means you've made an error somewhere along the line. All right, try this one on your own. See how you did. So off to the side here, I rewrote equations in the vector form, just to help see. The little green negative 3 above the s, that's just there to show you that if you plugged in negative 3, the point negative 9, 10 is on that line. You might be able to see by looking at the direction vectors that they're parallel as well. But often you don't see that and start setting things up to solve. So if you set up your parametric equations, from line 1, I have it in green, and in line 2, I have it in blue, which sets up your system of equations in black. I took equation 2 and multiplied it by 2 to eliminate the s's, and I get a statement that 11 is equal to 11, which you might want to add to your list of useful facts.
And 0 plus 0 is equal to negative 5.
That's right. So they are the same line, and if you think about them being parallel and sharing the same point, they have to be the same line. The last one we're going to do together. Determine if the lines, and this is in 3 dimensionals, are concurrent. And if they are, we're going to find their position vector. So our parametric equations from the first line are 2 plus t, 1 minus t, and t. From our second line, 3 plus 2s, 3s, negative 1 minus s. That gives us 3 equations with 2 unknowns. We've got 2 plus t is equal to 3 plus 2s. We have 1 minus t is equal to 3s, and we have that t is equal to negative 1 minus s. Now that's overkill. If you have 2 unknowns and 3 equations, you have too much information. In order to solve, you would just need 2 equations with 2 unknowns. And these equations are very nice. I hope you can see that t can cancel quite easily. If I take equation 1 and equation 2 and add them, I'm going to get 3 plus 0 equals 3 plus 5s. Can you see that? If I move things over, I get 0 is equal to 5s. So s has to be 0.
That means that doesn't count on the loop.
If s is 0, okay? Now I'm using equation 1 and equation 2. If s is 0, then t equals, I can plug in 0 for s either into equation 1 or equation 2. If I plug it into equation 2, Whoa, that was fancy. Just the heat of my hand moved it.
Let's see so much moisture in the air.
If I plug in 0 for S, can you see that T would have to be 1? Can you see in equation 1 and equation 2 that they work both?
Yeah.
When S is 0, T is 1, that works for equation 1. It works for equation 2. And it does not work for equation 3. So it's not enough to solve for S and T. You have to show that it also works for that third line. If it does not work for the third line, as in this case, these lines are skew.
Sounds like you're calling the lines crap.